Younger Dryas. Evolution of temperatures in the post-glacial period, after the last glacial maximum, showing very low temperatures for the most part of the Younger Dryas, rapidly rising afterwards to reach the level of the warm Holocene, based on Greenland ice cores. The Younger Dryas, which occurred circa 12,900 to 11,700 years BP, was a return to glacial conditions which temporarily reversed the gradual climatic warming after the last glacial maximum, which lasted from circa 27,000 to 20,000 years BP. The Younger Dryas was the last stage of the Pleistocene epoch that spanned from 2,580,000 to 11,700 years BP, and it preceded the current, warmer Holocene epoch. The Younger Dryas was the most severe and longest-lasting of several interruptions to the warming of the Earth's climate, and it was preceded by the Late Glacial Interstadial, also called the Balling-Allerod Interstadial, an interval of relative warmth that lasted from 14,670 to 12,900 BP. The change was relatively sudden, took place over decades, and resulted in a decline of temperatures in Greenland by 4 to 10 degrees Celsius, 7.2 to 18 degrees Fahrenheit, and advances of glaciers and drier conditions over much of the temperate northern hemisphere. A number of theories have been put forward about the cause, and the hypothesis historically most supported by scientists is that the Atlantic meridional overturning circulation, which transports warm water from the equator towards the North Pole, was interrupted by an influx of fresh, cold water from North America into the Atlantic. However, several issues do exist with this hypothesis, one of which is the lack of a clear geomorphological route for the meltwater. In fact, the originator of the meltwater hypothesis, Wallace Broecker, stated in 2010 that the long-held scenario that the Younger Dryas was a one-time outlier triggered by a flood of water stored in proglacial Lake Agassiz, has fallen from favor due to lack of a clear geomorphic signature at the correct time and place on the landscape. A volcanic trigger has been proposed more recently, and the presence of anomalously high levels of volcanism immediately preceding the onset of the Younger Dryas has been confirmed in both ice cores and cave deposits. The Younger Dryas did not affect the climate equally worldwide, but the average worldwide temperature changed drastically. For example, in the southern hemisphere and some areas of the northern hemisphere, such as southeastern North America, a slight warming occurred. The Younger Dryas is named after an indicator genus, the alpine tundra wildflower Dryas octopetala, as its leaves are occasionally abundant in late glacial, often minerogenic-rich sediments, such as the lake sediments of Scandinavia. General description and context. This image shows temperature changes, determined as proxy temperatures, taken from the central region of Greenland's ice sheet during the late Pleistocene and beginning of the Holocene. The presence of a distinct cold period at the end of the last glacial maximum has been known for a long time. Paleobotanical and lithostratigraphic studies of Swedish and Danish bog and lake sites, as in the Allerod clay pit in Denmark, first recognized and described the Younger Dryas. The Younger Dryas is the youngest and longest of three stadials, which resulted from typically abrupt climatic changes that took place over the last 16,000 years. Within the BLYTT Cernander classification of North European climatic phases, the prefix Younger refers to the recognition that this original Dryas period was preceded by a warmer stage, the Allerod Oscillation, which, in turn, was preceded by the Older Dryas, around 14,000 calibrated years BP. That is not securely dated, and estimates vary by 400 years, but it is generally accepted to have lasted around 200 years. In northern Scotland, the glaciers were thicker and more extensive than during the Younger Dryas. The Older Dryas, in turn, was preceded by another warmer stage, the Balling Oscillation, that separated it from a third and even older stadial, often known as the Oldest Dryas. The Oldest Dryas occurred about 1,770 calibrated years before the Younger Dryas and lasted about 400 calibrated years. According to the GISP2 ice core from Greenland, the Oldest Dryas occurred between about 15,070 and 14,670 calibrated years BP. In Ireland, the Younger Dryas has also been known as the Nahannigan Stadial, and in Great Britain it has been called the Loch Lomond Stadial. In the Greenland Summit Ice Core chronology, the Younger Dryas corresponds to Greenland Stadial 1, GS1. The preceding Allerod warm period, interstadial, is subdivided into three events: Greenland Interstadial 1C to 1A, GI1C to GI1A. Temperatures derived from Epica Dome Sea ice core in Antarctica. In addition to the Younger, Older, and Oldest Dryases, a century-long period of colder climate, similar to the Younger Dryas in abruptness, has occurred within both the Bolling Oscillation and the Allerod Oscillation interstadials. The cold period that occurred within the Bolling Oscillation is known as the intra-Bolling cold period, and the cold period that occurred within the Allerod Oscillation is known as the intra-Allerod cold period. Both cold periods are comparable in duration and intensity, with the older Dryas and began and ended quite abruptly. The cold periods have been recognized in sequence and relative magnitude in paleoclimatic records from Greenland ice cores, European lacustrine sediments, Atlantic Ocean sediments, and the Carayaco Basin, Venezuela. Examples of older-younger Dryas-like events have been reported from the ends, called terminations, of older glacial periods. Temperature-sensitive lipids, long-chain alkanones, found in lake and marine sediments, are well regarded as a powerful paleothermometer for the quantitative reconstruction of past continental climates. The application of alkanone paleothermometers to high-resolution paleotemperature reconstructions of older glacial terminations have found that very similar, younger Dryas-like paleoclimatic oscillations occurred during terminations 2 and 4. If so, the younger Dryas is not the unique paleoclimatic event, in terms of size, extent, and rapidity, as it is often regarded to be it. Furthermore, paleoclimatologists and quaternary geologists reported finding what they characterized as well-expressed younger Dryas events in the Chinese Delta 180 records of termination 3 in stalagmites from high-altitude caves in Shenanjia area, Hubei province, China. Various paleoclimatic records from ice cores, deep-sea sediments, speleothems, continental paleobotanical data, and lusses show similar abrupt climate events, which are consistent with younger Dryas events, during the terminations of the last 4 glacial periods, see Dansgaard-Oeschger event. They argue that younger Dryas events might be an intrinsic feature of deglaciations that occur at the end of glacial periods. Timing. Analyses of stable isotopes from Greenland ice cores provide estimates for the start and end of the younger Dryas. The analysis of Greenland summit ice cores, as part of the Greenland Ice Sheet Project 2 and Greenland Ice Core Project, estimated that the younger Dryas started about 12,800 ice, calibrated, years BP. More recent work with stalagmites strongly suggests a start date of 12,870 plus or minus 30 years BP, consistent with the more recent North Greenland Ice Core Project, NGRIP, ice core data. Depending on the specific ice core analysis consulted, the younger Dryas is estimated to have lasted 1,150 to 1,300 years. Measurements of oxygen isotopes from the GISP2 ice core suggest the ending of the younger Dryas took place over a period of about 50 years. Other proxy data, such as dust concentration and snow accumulation, suggest an even more rapid transition, lasting for 30 years or less, potentially as rapid as less than 20 years. Greenland experienced about 7 degrees Celsius 13 degrees Fahrenheit of warming in just half a century. Total warming in Greenland was 10 plus or minus 4 degrees Celsius, 18 plus or minus 7 degrees Fahrenheit. The end of the younger Dryas has been dated to around 11,550 years ago, occurring at 10,000 BP, uncalibrated radiocarbon year, a radiocarbon plateau by a variety of methods, mostly with consistent results. Years ago. Place. 11,500 plus or minus 50. Grip ice core, Greenland. 11530 plus 40 minus 60. Kraken's Lake, Western Norway. 11,570. Carayaco Basin Core, Venezuela. 11,570. German oak and pine dendrochronology. 11,640 plus or minus 280. GISP2 ice core, Greenland. The International Commission on Stratigraphy put the start of the Greenlandian stage, and implicitly the end of the younger Dryas, at 11,700 years before 2000. Although the start of the younger Dryas is regarded to be synchronous across the North Atlantic region, recent research concluded that the start of the younger Dryas might be time transgressive even within there. After an examination of laminated varve sequences, Muscatiello and Wolfarth found that the environmental changes that define the beginning of the younger Dryas are diachronous in their time of occurrence according to latitude. According to the changes, the younger Dryas occurred as early as around 12,900 to 13,100 calibrated years ago along latitude 56 of 54 degree N. Further north, they found that the changes occurred at roughly 12,600 to 12,750 calibrated years ago. Dryas stadials. According to the analyses of varved sediments from Lake Suigetsu, Japan, and other paleoenvironmental records from Asia, a substantial delay occurred in the onset and the end of the Younger Dryas between Asia and the North Atlantic. For example, paleoenvironmental analysis of sediment cores from Lake Suigetsu in Japan found the Younger Dryas temperature decline of 2 to 4 degrees Celsius between 12,300 and 11,250 varv, calibrated, years BP, instead of about 12,900 calibrated years BP in the North Atlantic region. In contrast, the abrupt shift in the radiocarbon signal from apparent radiocarbon dates of 11,000 radiocarbon years to radiocarbon dates of 10,700 to 10,600 radiocarbon years BP in terrestrial macrofossils and tree rings in Europe over a 50-year period occurred at the same time in the varved sediments of Lake Suigetsu. However, the same shift in the radiocarbon signal antedates the start of Younger Dryas at Lake Suigetsu by a few hundred years. Interpretations of data from Chinese also confirm that the Younger Dryas East Asia lags the North Atlantic Younger Dryas cooling by at least 200-300 years. Although the interpretation of the data is more murky and ambiguous, the end of the Younger Dryas and the start of Holocene warming likely were similarly delayed in Japan and in other parts of East Asia. Similarly, an analysis of a stalagmite growing from a cave in Puerto Princesa Subterranean River National Park, Palawan, the Philippines, found that the onset of the Younger Dryas was also delayed there. Proxy data recorded in the stalagmite indicate that more than 550 calibrated years were needed for Younger Dryas drought conditions to reach their full extent in the region and about 450 calibrated years to return to pre-Younger Dryas levels after it ended. In the Orca Basin in the Gulf of Mexico, a drop in sea surface temperature of approximately 2.4 plus or minus 0.6 degrees Celsius that lasted from 12,800 to 11,600 BP, as measured by mg/Ca ratios in the planktonic foraminifer Globigerinoides ruber, signifies the occurrence of the Younger Dryas in the Gulf of Mexico. Global effects. The Younger Dryas was globally synchronous or very nearly so. However, the magnitude of the drop in global mean surface temperature was modest. The Younger Dryas was not a global relapse into peak glacial conditions. In Western Europe and Greenland, the Younger Dryas is a well-defined synchronous cool period. Cooling in the tropical North Atlantic may, however, have preceded it by a few hundred years. South America shows a less well-defined initiation but a sharp termination. The Antarctic cold reversal appears to have started 1,000 years before the Younger Dryas and has no clearly defined start or end. Peter Hybers has argued that there is a fair confidence in the absence of the Younger Dryas in Antarctica, New Zealand, and parts of Oceania. Timing of the tropical counterpart to the Younger Dryas, the deglaciation climate reversal, DCR, is difficult to establish as low-latitude ice core records generally lack independent dating over the interval. An example of this is the Sajama ice core, Bolivia, for which the timing of the DCR has been pinned to that of the GISP2 ice core record, Central Greenland. Climatic change in the Central Andes during the DCR, however, was significant and was characterized by a shift to much wetter and likely colder conditions. The magnitude and abruptness of the changes would suggest that low-latitude climate did not respond passively during the YD/DCR. Carbon dioxide levels steadily increased over the course of the Younger Dryas, from circa 210 ppm at its start to circa 275 ppm at its termination. Methane clathrates remained stable over the course of the Younger Dryas. Effects of the Younger Dryas were of varying intensity throughout North America. In Western North America, its effects were less intense than in Europe or Northeast North America. Wink with a frown. However, evidence of a glacial readvance indicates that Younger Dryas cooling occurred in the Pacific Northwest. Speleothems from the Oregon Caves National Monument and Preserve in southern Oregon's Klamath Mountains yield evidence of climatic cooling contemporaneous to the Younger Dryas. Other features include the following: replacement of forest in Scandinavia with glacial tundra, which is the habitat of the plant Dryas octopetala. Glaciation or increased snow in mountain ranges around the world. Formation of solifluction layers and loess deposits in northern Europe. More dust in the atmosphere, originating from deserts in Asia. A decline in evidence for Natufian hunter-gatherer permanent settlements in the Levant, suggesting a reversion to a more mobile way of life. The well-known Mascardi cold reversal in the southern hemisphere ended at the same time. Decline of the Clovis culture, While no definitive cause for the extinction of many species in North America such as the Columbian mammoth, as well as the dire wolf, camelops, and other Rhyncholabrian megafauna during the Younger Dryas has been determined, climate change and human hunting activities have been suggested as contributing factors. Recently, it has been found that these megafauna populations collapsed 1,000 years earlier. North America, Greenland. Despite cold conditions, Greenlandic glaciers retreated during the Younger Dryas, with the exception of some local glaciers in northern Greenland. This was most likely due to a weakening of the Atlantic meridional overturning circulation, AMOZ. East. The Younger Dryas is a period significant to the study of the response of biota to abrupt climate change and to the study of how humans cope with such rapid changes. The effects of sudden cooling in the North Atlantic had strong regional effects in North America, with some areas experiencing more abrupt changes than others. A cooling and ice advance accompanying the transition into the Younger Dryas between 13,300 and 13,000 calories years BP has been confirmed with many radiocarbon dates. From 4 sites in western New York State, the advance is similar in age to the Two Creeks forest bed in Wisconsin. The effects of the Younger Dryas cooling affected the area that is now New England and parts of maritime Canada more rapidly than the rest of the present-day United States at the beginning and the end of the Younger Dryas chronozone. Proxy indicators show that summer temperature conditions in Maine decreased by up to 7.5 degrees Celsius. Cool summers, combined with cold winters and low precipitation, resulted in a treeless tundra up to the onset of the Holocene, when the boreal forests shifted north. Vegetation in the central Appalachian Mountains east towards the Atlantic Ocean was dominated by spruce, Picea spp, and tamarack, Larix laricina, boreal forests that later changed rapidly to temperate, more broadleaf tree forest conditions at the end of the Younger Dryas period. Conversely, pollen and macrofossil evidence from near Lake Ontario indicates that cool, boreal forests persisted into the early Holocene, west of the Appalachians, in the Ohio River Valley and south to Florida Rapid. No analog vegetation responses seem to have been the result of rapid climate changes, but the area remained generally cool, with hardwood forest dominating. During the Younger Dryas, the southeastern United States was warmer and wetter than the region had been during the Pleistocene. Because of trapped heat from the Caribbean within the North Atlantic gyre caused by a weakened AMOZ. Central. Also, a gradient of changing effects occurred from the Great Lakes region south to Texas and Louisiana. Climatic forcing moved cold air into the northern portion of the American interior, much as it did the Northeast. Although there was not as abrupt a delineation as seen on the eastern seaboard, the Midwest was significantly colder in the northern interior than it was south, towards the warmer climatic influence of the Gulf of Mexico. In the north, the Laurentide ice sheet re-advanced during the Younger Dryas, depositing a moraine from West Lake Superior to southeast Quebec. Along the southern margins of the Great Lakes, spruce dropped rapidly, while pine increased, and herbaceous prairie vegetation decreased in abundance, but increased west of the region. Rocky Mountains. Effects in the Rocky Mountain region were varied. In the northern Rockies, a significant increase in pines and firs suggests warmer conditions than before and a shift to subalpine parkland in places. That is hypothesized to be the result of a northward shift in the jet stream, combined with an increase in summer insolation, as well as a winter snowpack that was higher than today, with prolonged and wetter spring seasons. There were minor re-advancements of glaciers in place, particularly in the northern ranges, but several sites in the Rocky Mountain ranges show little to no changes in vegetation during the Younger Dryas. Evidence also indicates an increase in precipitation in New Mexico because of the same Gulf conditions that were influencing Texas. West. The Pacific Northwest region experienced 2 to 3 degrees Celsius of cooling and an increase in precipitation. Glacial re-advancement has been recorded in British Columbia, as well as in the Cascade Range. An increase of pine pollen indicates cooler winters within the Central Cascades. On the Olympic Peninsula, a mid-elevation site recorded a decrease in fire, but forest persisted and erosion increased during the Younger Dryas, which suggests cool and wet conditions. Speleothem records indicate an increase in precipitation in southern Oregon, the timing of which coincides with increased sizes of pluvial lakes in the northern Great Basin. Pollen record from the Siskiyou Mountains suggests a lag in timing of the Younger Dryas, indicating a greater influence of warmer Pacific conditions on that range, but the pollen record is less chronologically constrained than the aforementioned speleothem record. The southwest appears to have seen an increase in precipitation, as well, also with an average 2 degrees Celsius of cooling. Central America. In Costa Rica, rapid swings in temperature at the end of the Younger Dryas closely tracked and matched those observed in Greenland's ice cores, suggesting a common, synchronous cause for these oscillations. Europe. Since 1916 and the onset and the subsequent refinement of pollen analytical techniques and a steadily growing number of pollen diagrams, palynologists have concluded that the Younger Dryas was a distinct period of vegetational change in large parts of Europe during which vegetation of a warmer climate was replaced by that of a generally cold climate, a glacial plant succession that often contained Dryas octopetala. The drastic change in vegetation is typically interpreted to be an effect of a sudden decrease in annual temperature, unfavorable for the forest vegetation that had been spreading northward rapidly. The cooling not only favored the expansion of cold-tolerant, light-demanding plants and associated steppe fauna, but also led to regional glacial advances in Scandinavia and a lowering of the regional snowline. The change to glacial conditions at the onset of the Younger Dryas in the higher latitudes of the northern hemisphere, between 12,900 and 11,500 calibrated years BP, has been argued to have been quite abrupt. It is in sharp contrast to the warming of the preceding older Dryas interstadial. Its end has been inferred to have occurred over a period of a decade or so, but the onset may have even been faster. Thermally fractionated nitrogen and argon isotope data from Greenland ice core GISP2 indicate that its summit was around 15 degrees Celsius 27 degrees Fahrenheit colder during the Younger Dryas than today. In Great Britain, the mean annual temperature was no higher than -1 degree Celsius -1.8 degrees Fahrenheit as indicated by the presence of permafrost, and beetle fossil evidence suggests that the mean annual temperature dropped to -5 degrees C, 23 degrees Fahrenheit, and periglacial conditions prevailed in lowland areas, and ice fields and glaciers formed in upland areas. Sea ice influences on seasonality fostered exceptional aridity in Scotland. Nothing of the period's size, extent, or rapidity of abrupt climate change has been experienced since its end. In what is now Hesse, the early part of the Younger Dryas saw the development of a multi-channel braid plain. During the later Younger Dryas, this braid plain reverted back to a fluvial system of straight and meandering rivers akin to that which had been the norm during the Allerrad Oscillation. In the Dinaric Alps, various lateral and terminal moraines have been dated to have been formed during the Younger Dryas and associated resurgence of glaciers. Evidence from the Jablanica mountain indicates that aridity fostered continued glacial retreat despite the cold temperatures of the Younger Dryas. Middle East. Anatolia was extremely arid during the Younger Dryas. No intensification of geomorphodynamic activity occurred around Göbekli Tepe at the terminus of the Younger Dryas. East Asia. Pollen records from Lake Gonghai in Shaanxi, China show a major increase in aridity synchronous with the onset of the Younger Dryas, believed by some scholars to be a consequence of a weakened East Asian summer monsoon, EASM. Some studies, however, have concluded that the EASM instead strengthened during the Younger Dryas. Africa. Lake Tanganyika experienced a decline in wind-driven seasonal mixing, a phenomenon attributable to the more southerly position of the Intertropical Convergence Zone, ITCZ, and a weakened southwest Indian monsoon. Effects on agriculture. The Younger Dryas is often linked to the Neolithic Revolution, with the adoption of agriculture in the Levant. The cold and dry Younger Dryas arguably lowered the carrying capacity of the area and forced the sedentary early Natufian population into a more mobile subsistence pattern. Further climatic deterioration is thought to have brought about cereal cultivation. While relative consensus exists regarding the role of the Younger Dryas in the changing subsistence patterns during the Natufian, its connection to the beginning of agriculture at the end of the period is still being debated. Sea level. Based upon solid geological evidence, consisting largely of the analysis of numerous deep cores from coral reefs, variations in the rates of sea level rise have been reconstructed for the post-glacial period. For the early part of the sea level rise that is associated with deglaciation, 3 major periods of accelerated sea level rise, called meltwater pulses, occurred. They are commonly called meltwater pulse 1 is 0 for the pulse between 19,000 500 calibrated years ago. Meltwater pulse 1a for the pulse between 14,614 300 calibrated years ago. Meltwater pulse 1b for the pulse between 11,411 100 calibrated years ago. The younger Dryas occurred after meltwater pulse 1a, a 13.5 m rise over about 290 years, centered at about 14,200 calibrated years ago, and before meltwater pulse 1b, a 7.5 m rise over about 160 years, centered at about 11,000 calibrated years ago. Finally, not only did the younger Dryas postdate both all of meltwater pulse 1a and predate all of meltwater pulse 1b, it was a period of significantly reduced rate of sea level rise relative to the periods of time immediately before and after it. Possible evidence of short-term sea level changes has been reported for the beginning of the younger Dryas. First, the plotting of data by Bard and others suggests a small drop, less than 6 m, in sea level near the onset of the younger Dryas. There is a possible corresponding change in the rate of change of sea level rise seen in the data from both Barbados and Tahiti. Given that this change is within the overall uncertainty of the approach, it was concluded that a relatively smooth sea level rise, with no significant accelerations, occurred then. Finally, research by Lohe and others in western Norway has reported a sea level low stand at 13,640 calibrated years ago and a subsequent younger Dryas transgression starting at 13,080 calibrated years ago. They concluded that the timing of the Alarad low stand and the subsequent transgression were the result of increased regional loading of the crust, and geoid changes were caused by an expanding ice sheet, which started growing and advancing in the early Alarad, about 13,600 calibrated years ago, well before the start of the younger Dryas. Ocean circulation. The younger Dryas resulted in decreased ventilation of ocean bottom waters. Cores from the western subtropical North Atlantic show that the ventilation age of the bottom water there was about 1,000 years, twice the age of late Holocene bottom waters from the same site around 1,500 BP. Cause. The younger Dryas has historically been thought to have been caused by significant reduction or shutdown of the North Atlantic conveyor, which circulates warm tropical waters northward, as the consequence of deglaciation in North America and a sudden influx of fresh water from Lake Agassiz. The lack of geological evidence for such an event stimulated further exploration, but no consensus exists on the precise source of the freshwater, and in fact the freshwater pulse hypothesis has recently been called into question. Although originally the freshwater pathway was believed to be the St. Lawrence Seaway, the lack of evidence for this route has led researchers to suggest alternative sources for the freshwater, including a pathway along the Mackenzie River, deglacial water coming off of Scandinavia, the melting of sea ice, increased rainfall, or increased snowfall across the North Atlantic. The global climate would then have become locked into the new state until freezing removed the freshwater lid from the North Atlantic. However, simulations indicated that a one-time flood could not likely cause the new state to be locked for 1,000 years. Once the flood ceased, the amok would recover and the younger Dryas would stop in less than 100 years. Therefore, continuous freshwater input would be necessary to maintain a weak AMOC for more than 1,000 years. A 2018 study proposed that the snowfall could be a source of continuous freshwater resulting in a prolonged weakened state of the AMOC. The lack of consensus regarding the origin of the freshwater, combined with the lack of evidence for sea level rise during the younger Dryas, are problematic for any hypothesis where the younger Dryas was triggered by floodwater. It is often noted that the younger Dryas is merely the last of 25 or 26 major climate episodes, Dansgaard-Oshker events, or DO events, over the past 120,000 years. These episodes are characterized by abrupt beginnings and endings, with changes taking place on timescales of decades or centuries. The younger Dryas is the best known and best understood because it is the most recent, but it is fundamentally similar to the previous cold phases over the past 120,000 years. Based on the fact that the younger Dryas is extremely similar in structure with previous cold phases not thought to have been caused by meltwater pulses, it has been argued that understanding the causes of the younger Dryas would benefit from examining the mechanisms used to explain DO events rather than relying on the meltwater hypothesis. Another idea is that a solar flare may have been responsible for the megafaunal extinction that occurred at approximately the same time as the younger Dryas, but that cannot explain the apparent variability in the timing of the extinction across all continents. The younger Dryas impact hypothesis attributes the cooling to the impact of a disintegrating comet or asteroid, but that idea is rejected by most experts, though it is promoted by pseudoscientific archaeology television. An increasingly well-supported alternative to the meltwater trigger is that the younger Dryas was triggered by volcanism. Numerous papers now confidently link volcanism to a variety of cold events across the last 2 millennia, and the Holocene, and in particular several note the ability of volcanic eruptions to trigger climate change lasting for centuries to millennia. It was proposed that a high-latitude volcanic eruption could have shifted atmospheric circulation sufficiently to increase North Atlantic sea ice growth and slow down AMOC, subsequently leading to a positive cooling feedback and initiating the Younger Dryas. This perspective is now supported by evidence for volcanism coinciding with the start of the Younger Dryas from both cave deposits and glacial ice cores. Particularly strong support comes from sulfur data from Greenland ice cores showing that the radiative forcing associated with the cluster of eruptions immediately preceding the Younger Dryas initiation exceeds the most volcanically active periods during the Common Era, which experienced notable multi-decadal scale cooling commonly attributed to volcanic effects. Notably, the sulfur data strongly suggests that a very large and high-latitude northern hemisphere eruption occurred 12,870 years ago, a date indistinguishable from the stalagmite-derived onset of the Younger Dryas event. It is unclear which eruption was responsible for this sulfur spike, but the characteristics are consistent with the Lacher Sea eruption as the source. The eruption was dated to 12,880 plus or minus 40 years BP by Varv counting sediment in a German lake, and to 12,900 plus or minus 560 years by 40 AR/39 AR dating, both of which are within dating uncertainties of the sulfur spike at 12,870 years BP, and make the Lacher Sea eruption a possible trigger for the Younger Dryas. However, a new radiocarbon date challenges the previous dating for the Lacher Sea eruption, moving it back to 13,006 years BP, but this date itself has been challenged as potentially having been affected by radiocarbon-dead magmatic carbon dioxide, which was not accounted for and made the date appear older than it was. Regardless of the ambiguity surrounding the date for the Lacher Sea eruption, it almost certainly caused substantial cooling either immediately before the Younger Dryas event, or as one of the several eruptions which clustered in the 100 years preceding the event. A volcanic trigger for the Younger Dryas event also explains why there was little sea level change at the beginning of the event. Furthermore, it is also consistent with previous work that links volcanism with DO events, and with the perspective that the Younger Dryas is simply the most recent DO event. It is worth noting that of the proposed Younger Dryas triggers, the volcanic trigger is the only one with evidence that is almost universally accepted as reflecting the actual occurrence of the trigger. No consensus exists that a meltwater pulse happened, or that a bolide impact occurred prior to the Younger Dryas, whereas the evidence of anomalously strong volcanism prior to the Younger Dryas event is now very strong. Outstanding questions include whether a short-lived volcanic forcing can trigger 1,300 years of cooling, and how background climate conditions affect the climate response to volcanism. End of the Younger Dryas. The end of the Younger Dryas was caused by an increase in carbon dioxide levels and a shift in Atlantic meridional overturning circulation. Evidence suggests that most of the increase in temperature between the last glacial maximum and the Holocene took place in the immediate aftermath of the oldest Dryas and Younger Dryas, with there being comparatively little variations in global temperature within the oldest and Younger Dryas periods and within the Balling-Alarod warming.